Welcome to the second lesson on astrophysics and cosmology. In this lesson, we are going to try and achieve the following outcomes, namely, explain that in a stable star there is an equilibrium between radiation pressure and gravitational pressure, and then using Wien's displacement law to determine the peak surface temperature of a star from the peak wavelength, either graphically or algebraically. So these are the two learning outcomes that we are going to aim to achieve in this lesson. So what makes a star stable? Well, in a stable star, there are two main types of pressure that exist. The first one is an inward pressure, namely the gravitational pressure, which is caused by the huge gravitational forces that are trying to collapse the star. So stars are extremely huge bodies of gas and plasma, and because of all the matter that is in a star, there is a net gravitational attraction toward the center of the star. Now, because of the fact that stars are so huge, this gravitational force is huge, and so therefore the associated gravitational pressure is huge, and so it causes immense pressure at the core of a star. The second type of pressure is known as radiation pressure. Now, this is caused by the energy released by every proton-proton cycle, and as the released photons move outwards, they collide with the surrounding material, creating radiation pressure. So this is the pressure that is created by nuclear fusion, and it's an outward pressure because due to the immense gravitational pressure and the huge temperatures of the order of millions of degrees Celsius in the center of stars, we find that the nuclei fuse, the protons, the nuclei of hydrogen atoms fuse through the process of proton-proton cycle, and then remember we also in larger stars the CNO cycle, and this causes photons to move outward. Now, as they move outward, they collide with the material and heat the material up, and so this is the outward pressure is the radiation pressure. So these pressures work against each other. Adding to this, we also have convection currents in the outer layers of the star, and they also carry energy outwards, adding to the radiation pressure. So the radiation pressure is moving outwards like this against the gravitational pressure. So in a stable star, there's an equilibrium between the outward radiative pressure, the PR, against the gravitational pressure, which is acting inwards. So when there is a balance between the outward radiative pressure and the inward gravitational pressure, then there is equilibrium, and therefore one has a stable system and a stable star. Now, when astronomers look into the universe and they look at stars and they look at them in detail, they find that stars come in different colors, and these differences in colors, as we will see, is based on their temperatures. Now, in the constellation Orion, there are two stars that we're going to focus on, namely Rigel. There are other stars as well, but the two stars we're going to focus on are Rigel, which is a bright blue, bluish-white star, which we see in the top right-hand corner of this photograph. And then we have Betelgeuse, which is a bright yellow-orange star that's in the bottom left. Now, these two stars are very different from each other, as we will see, and they have very different colors because of the fact that they have very different surface temperatures. Now, in a laboratory on Earth, if we look at Bunsen burner flames that are burning at different temperatures, and if you've ever used a Bunsen burner, and I sincerely hope that you have, the way we increase the temperature is by adding more oxygen, by opening the collar of the Bunsen burner more and more and more. Now, as you open the collar of the Bunsen burner, you see that the temperature, the color varies and the temperature varies. So in this diagram here, the coolest flame is the yellowish flame on the left. We see here, and that burns at around about 800 to 900 degrees Celsius, whereas these bluish violet like flames are very much hotter. They're in the thousands of degrees Celsius, and so as we go from left to right here, the temperature is increasing. So color is definitely dependent on temperature. So temperature is proportional to the kinetic energy of particles. So as the temperature increases, so the average kinetic energy of the particles increases, which implies that the particles are moving faster on average. Now, in grade 10, you should have learned that accelerating charged particles lead to electromagnetic radiation. Now, in a flame, it's in a plasma-like state, and so you have free charge, free electrons and free charged ions, positively charged ions that are moving around. In particular, it's the electrons that give off the light that we observe. Now, the electromagnetic spectrum, as shown in this figure, we've learnt in grade 10, or should have learnt in grade 10. It ranges from radio waves, which have extremely long wavelengths of the order of 10 to the 3 meters. So it can be meters to kilometers. Then as we move from left to right, from the large wavelengths to the smaller wavelengths, we get microwave, we get infrared, then we get visible light, which is red, orange, yellow, green, blue, indigo, violet. We get ultraviolet, we get X-rays, and we get gamma rays. And here the order of magnitude is 10 to the minus 12, 10 to the minus 15, which is the order of magnitude of the size of a nucleus. So the electromagnetic spectrum has a huge variance in wavelength and obviously frequency. Now, if we look at the associated temperatures of objects at which this radiation is the most intense wavelength emitted, then we can see there's a definite relationship between the temperature and the actual electromagnetic radiation, the peak electromagnetic radiation. So we can see with visible light that we're looking anywhere between 100 Kelvin to up to about 10,000 Kelvin, which is about 9,727 degrees Celsius. So we are going to explore this in more detail. So to summarize, we can see that the type of electromagnetic radiation is determined by how fast the particles are moving, which is dependent upon the average kinetic energy of the particles. So the higher the kinetic energy, the higher the temperature, the higher the frequency. Now, with electromagnetic radiation, as you should have learnt in grade 10, energy of the photons of electromagnetic radiation is equal to Planck's constant multiplied by the frequency. So the energy of photons is directly proportional to the frequency of the electromagnetic radiation. So if the wavelength is smaller, this implies light given off is in the blue portion of the visible section of the electromagnetic spectrum, where the frequency is higher and the energy of the photons is higher. If there's a lower kinetic energy, then it implies that there's a lower temperature, a lower frequency, which implies the lambda is larger or longer, which implies that the light given off is in the red portion of the visible section of the electromagnetic spectrum. For the sake of enrichment, this was not going to be assessed formally in tests and examinations. We just want to look at two relationships. So the average kinetic energy of a system of particles is equal to 3/2, or 1/2, multiplied by Boltzmann's constant, which is 1,380649, multiplied by 10 to the negative 3 joules per coulomb, multiplied by the absolute temperature. So we can see here that average kinetic energy is dependent on temperature. And the higher the temperature, the higher the average kinetic energy. So now, looking at the Maxwell-Boltzmann distribution, which you will also look at in chemical kinetics in your grade 11 syllabus, if you look at the number of particles in a system and you look at their kinetic energy, the distribution of their kinetic energy, when you've got a cold body with a lower temperature, then you find that the distribution has got a narrower peak, and the peak is at a lower kinetic energy. So we've looked here and identified that because the average kinetic energy is directly dependent on the temperature, if the temperature is low, the average kinetic energy is going to be low, as we can see here. And likewise, if the average kinetic energy is high, then that's going to mean that the temperature is high, or vice versa. If the temperature is high, the average kinetic energy is going to be high. So then the average kinetic energy will sit here for a hot body at a particular temperature, which is much higher than for when the body is at a lower temperature. Then we can see also that there's a greater spread of the energies. Now, Boltzmann and Maxwell set up this equation, which defines or describes mathematically this probability distribution. And so if you go further with your studies in physics and you go and you study statistical physics in second and third year physics at university, then you will come across this relationship. So this shows us that the frequency of electromagnetic radiation emitted by an object corresponds to its temperature. So it follows that Betelgeuse, which radiates in the orange-yellow portion of the electromagnetic spectrum, is much cooler than Rigel, which emits more in the blue-white section here of the spectrum. So there's a qualitative way of discerning the relative temperatures of stars in comparison to each other. But now we're going to look at a more quantitative way of doing so. Now, stars emit many wavelengths of electromagnetic radiation, not only one, and that's because of the fact that in stars they are made up of plasma, and in plasmas you have free electrons and you have free protons. So they're not in a bound state, so you're going to find that all sorts of wavelengths are going to be emitted due to the various accelerations and vibrations of the electrons and the protons. Now, all the wavelengths emitted by a particular star do not have the same intensity though. And when you plot the intensity versus wavelength of electromagnetic radiation emitted by a star, it gives us a characteristic graph called a black body curve. Now, a black body is a theoretical object that absorbs and emits all electromagnetic frequencies. So it is an ideal absorber and emitter of electromagnetic radiation. Now, the electromagnetic radiation from a star does not follow this curve exactly, but the black body curve is a very good first approximation to the actual spectrum, as we're going to see. So here we have the actual spectral curve of the Sun, and it is the jagged curve. So the solid curve is the electromagnetic spectrum of the Sun. And then what we have is the associated, the best fit black body curve, which is in the dotted blue. And so that is the theoretical black body that would best fit the electromagnetic spectrum of the Sun. Now we can work out what that particular associated temperature is of a black body to produce that curve. Now note that the peak curve of the Sun is around about 490 nanometers, which is in actual fact green light. So we can now, when we look at the black body that would give us this shape, we find that it is a black body associated with a temperature of about 5,800 Kelvin, which gives us an indication that the surface of the Sun is approximately 5,800 Kelvin. Now here we have a plot of spectral intensity versus wavelength for different stars, now with different surface temperatures. So we can see that when the temperature increases, we can see that the peak at which the wavelength at which the peak occurs, the peak intensity, that wavelength actually moves to the left. We can see here's a black body of 3,500 Kelvin. Here's a black body at 4,000 Kelvin, at 4,500, at 5,000 and 5,500. Now note that the peak wavelengths are moving to the left. But that means then that the associated frequencies are increasing, and as we know that energy is dependent, directly proportional to frequency, equals HF. So the frequency is going up, the energy is going up. We also see here that this peak sits outside of the visible range. This is the visible range. We can see here that this sits in the infrared region, so it's obviously got a wavelength bigger than the wavelength of red light. Here's the UV range, so we find here that, well, we see here that these peaks that we have here, they're, bar this one here, are all producing peaks that sit in the visible range between red light and violet light. So we now have a means to determine the temperatures of stars, and we're now going to move into a quantitative model known as Wien's displacement law. So Wien's displacement law, we're not going to look at the derivation of it, but basically it says that lambda 0, where lambda 0 is the peak wavelength at which the maximum power in the spectrum is to be found, and notice that the lambda will obviously be measured in meters. So where the peak intensity is, that wavelength in meters is symbolized by lambda 0, and then lambda 0 multiplied by the absolute temperature of the black body object is going to give us 2,90 times 10 to the negative 3 Kelvin multiplied by meters. Now if you look at the units, you do unit analysis, the wavelength is in meters, it's an absolute temperature in Kelvin, so these two quantities are being multiplied together, so the unit would be Kelvin meters. So let's consider the first example, and this one states that a star radiates most of its energy at a wavelength of 650 nanometers, which is in the visible spectrum. Calculate the surface temperature of the star. So if we were to plot the intensity of radiation at each wavelength versus the wavelength, then we would get a black body curve like this. We find that the peak intensity would be at a wavelength of 650 nanometers. So using Wien's displacement law, writing it down, lambda 0 multiplied by capital T, absolute temperature, equals 2,90 times 10 to the negative 3 Kelvin meters. We now substitute the peak wavelength, 650 nanometers is 650 times 10 to the negative 9 meters multiplied by T equals 2,90 times 10 to the negative 3 Kelvin meters. Dividing by 650 times 10 to the negative 9 meters on both sides means we take it downstairs. So the absolute temperature equals 2,90 times 10 to the negative 3 over 650 times 10 to the negative 9. And notice now what's going to happen with the meters. They are going to cancel, giving us an answer of the temperature, the surface temperature, being 4,461,538 Kelvin. Let's consider a second example. The star Sirius is the brightest in the night sky. It has a surface temperature of 9,940 Kelvin. Calculate the peak emission wavelength of Sirius. I ask that you pause the video here and that you use Wien's displacement law in order to try and solve this problem. And once you've done that, you can then check the solution by carrying on with the video, as I will provide the solution after this slide. So what we have here is we have a black body curve. We know that the temperature is 9940 Kelvin, so we are looking for the wavelength where the peak intensity is, and so we're now going to use Wien's displacement law. So writing it down, lambda 0 T equals 2,9 times 10 to the negative 3 Kelvin meters. We now have the temperature, so we substitute the Kelvin temperature in place of capital T. So we have lambda 0 multiplied by 9940 Kelvin equals 2,90 times 10 to the negative 3 Kelvin meters. We now divide both sides by 9,940 Kelvin to make lambda 0 the subject of the formula, and we get that 2,90 times 10 to the negative 3 Kelvin meters equals 9940 Kelvin. You're going to see that the Kelvin cancels top and bottom, giving us that lambda 0 equals 2,918 times 10 to the negative 7 meters. We can also write this as 291,8 times 10 to the negative 9. So what we've done is we've moved the comma 2 places to the right, which means then we must subtract by 2 in the index. So this 291,8 times 10 to the negative 9 meters is equivalent to 291,8 nanometers, which means that the peak wavelength is actually sitting outside of the visible range, because the visible range runs between 390 and about 790 nanometers. So this is going to be more toward the ultraviolet range of the electromagnetic spectrum. Now we're going to consider the third and final example in this lesson, namely, consider the following black body curve, this one here. From the curve, calculate the surface temperature of the star. Now, I would like you to pause the video here, as we did with example 2. And I would like you to try this example by interpreting the information given to you on the graph, on the black body distribution, and using Wien's law, and see if you can calculate the surface temperature of the star. So if we look at where the peak intensity is, then, and we go down to the wavelength axis, we see that where the peak is, the wavelength is 0,513, and when we look here, we see that the unit for 0,513 along this axis, the unit is micrometers, which is 10 to the negative 6 meters, or 1,000 nanometers, but we're going to look at 10 to the negative 6 meters. So this peak wavelength, which we can see is sitting in the visible range, is 0,513 times 10 to the negative 6 meters. So I've written it down there. Lambda 0 is equal to 0,513 micrometers, or 0,513 times 10 to the negative 6 meters. So now we are looking for the associated temperature that would provide a black body curve, or would produce a black body curve with a peak wavelength at 0,513 times 10 to the negative 6 meters. So we're going to use Wien's law. So Wien's displacement law, as we write it down, and remember the displacement we're talking about is the displacement of the peak intensity and the associated wavelength as the temperature of the body varies. So we've written it down here, lambda 0 T equals 2,9 times 10 to the negative 3 Kelvin meters. So we substitute for the peak wavelength 0,513 times 10 to the negative 6 meters multiplied by the temperature equals 2,9 times 10 to the negative 3 Kelvin meters. We now divide both sides by 0,513 times 10 to the negative 6 meters. So we take it down there, in order to make T the subject of the formula. So T equals 2,90 times 10 to the negative 3 Kelvin meters over 0,513 times 10 to the negative 6 meters. So the meters are going to cancel out. And that gives us an associated temperature of 5,653,021 Kelvin. So you can see from these three examples that by using Wien's displacement law, we can determine the average temperature of the surface of a star by looking at the distribution of its wavelengths, or intensity of wavelengths versus wavelengths for that particular star, and looking at the associated black body curve that would produce that shape and that peak wavelength.